Towards the end of the last lecture, we were considering the case of a long hollow composite cylinder. We were considering this case, and you will recall that we had derived expressions for the thermal resistance of the long hollow composite cylinder, which consisted of two materials with conductivities K1 and K2. We had derived an expression for the overall heat transfer coefficient for this cylinder, and we had an expression for the heat flow rate. So, we had an expression for RTH, the total thermal resistance of the long composite cylinder. We had an expression for the overall heat transfer coefficient, and you will also recall that since the area through which the heat is flowing goes on increasing as you go radially outwards, we have to specify on what area we are basing the overall heat transfer coefficient. So, we had derived expressions say for the radius R1, which is the inner radius of the tube on which the inner cylinder, or we could have put based u even on the outer radius R3, etc. So, we had expressions for RTH and for UR1, and once we have these expressions, you can calculate Q, the heat flow rate, as being equal to, if you want to use RTH, you will say simply Q is equal to Ti minus To, the temperature difference at the two extremes from inside to outside, divided by the RTH, or we can also say Q is nothing but UR1 multiplied by the area 2 pi R1 L multiplied by the temperature difference Ti minus To. All right. So, once we have an expression either for RTH or UR1, we can write down the heat flow rate through that long composite cylinder. This is where we stopped last time. Now, we are therefore in a position to consider, we are therefore now in a position to take up composite cases, that is, cases where a number of thermal resistances occur in series. Now, I want to make an important statement which is written down here, and I will read it slowly. The statement is as follows. It says, when several resistances occur in series, as in a long composite cylinder with two solid materials, we had four thermal resistances, one associated with Hi, one associated with the thermal conductivity K1, one associated with the thermal conductivity K2, and finally, the one associated with the outside heat transfer coefficient HO. You understand? Or with the infinite slab, where we took three solid materials, we had five thermal resistances. So, for any such situation, when several resistances occur in series, a few may be negligible compared to the others. An important aspect in many heat transfer problems is to identify the significant resistances and to ignore the insignificant ones. All right. When you have a number of thermal resistances in series, very often one or two or a few may be negligible. It is important, if you are a good engineer, that you should be able to identify which are the significant resistances and which are the insignificant resistances. So, this is an important statement which I am making. Now, in order to understand the significance of this statement, let us do the following problem. We are going to do a problem, and that is the following. Let us say, let us go back Let us go back to the earlier problem that we solved. You recall the earlier problem in which we had a tube with an inner diameter of 2 centimeters and an outer diameter of 4 centimeters. One surface was at 70 degrees centigrade, one was at 100 degrees centigrade, and for that tube we found out the rate at which heat was flowing, and we got an answer in that problem. Recall, in the earlier problem, we got the answer Q by L is equal to minus 157.7 watts per meter. You recall this problem. Now, I am going to change the data of this problem very slightly. We are going to change the data of the problem slightly. Instead of the outer surface being at a specified temperature T0, all right, it is now specified, instead of T0 being specified, T0 was specified to be 100, remember, it is now specified that saturated steam at 100 degrees centigrade is condensing on the outer surface. All right. That is the change in the input data that I am making. Saturated steam at 100 degrees centigrade is condensing on the outer surface of the tube. That is the change that I am making. All other data is the same. That means, what is the other data? The other data is, for instance, the ID of the tube. All other data ID of the tube, OD of the tube, all right, the thermal conductivity K of the material of the tube, the temperature Ti also remain the same. Find Q by L. Find Q by L. All right, that is the change. Now, how do we proceed now? First of all, let me just draw a rough sketch compared to the, so that we get the picture in front of us. Here is the tube, the center line, let us say this is the inner diameter, this is the outer diameter, all right, and this would be R . Outer radius, inner radius and outer radius. We are given the values RO and RI. This is RO equal to, I think, 2 centimeters, yes. This is RI equal to 1 centimeter. Okay. This is the solid material of the tube. K is given to be 0.58. And now, On the outer surface, we have steam condensing. So, the steam is going to condense and form a water film on the outside. So, on the outside here, you are going to have a water film. On the outer surface, you are going to have a water film formed by condensing steam. All right, formed by condensing steam at 100 degrees centigrade. That is what you are going to have. The inner surface remains at 70 degrees centigrade. The inner surface is this, that remains Ti equal to 70 degrees centigrade. Okay. That is the position. Now, what is the change compared to earlier? Earlier, from Ti to To, that is from 70 to 100, there was only one thermal resistance, and that thermal resistance was the thermal resistance of the tube. Now, we have got two thermal resistance in the path of the heat flow when it is flowing between the temperature difference 70 from inside to 100 on the outside. And what are the two thermal resistances? First, there are now two thermal resistances in the path of the heat flow. There are two thermal resistances in the path of the heat flow. And what are the two thermal resistances in the path of the heat flow? The two thermal resistances in the path of the heat flow are, let us write them down. Number 1, the two thermal resistances in the path of the heat flow are, number 1, the thermal resistance of the tube, the thermal resistance of the tube, all right, and secondly, the thermal resistance of the water film, the thermal resistance of the water film on the outside. Let us estimate the two. Let us put down values for them. RTH, thermal resistance of the tube, the first one, of the tube per meter, that is equal to log to the base E Rho by Ri, log to the base E Rho by Ri divided by 2 pi K L. We know that, all right. So, if you substitute the data, the given data, that is log to the base E 2 by 1 Rho by Ri divided by 2 pi into 0.58, the same thermal conductivity as earlier, into a meter length 1, that comes to 0.190 Kelvin per watt. All right. Thermal resistance of the condensate film per meter, thermal resistance of the condensate film, the water film of the condensate film per meter. Next, what is that? That is equal to 1 upon H A, 1 upon A. What is A? Pi DOL, that is A, multiplied by HO, that is equal to 1 upon pi into DO is 0.04, 4 centimeters, into length we will take as 1 meter length into HO. Now, HO is the heat transfer coefficient associated with the change of phase, that is condensation taking place on the outside of the tube. Let us take a typical value. A typical value of HO, I have already told you, would be in thousands, 5,000, 10,000 typical values. Let us take 5,000, all right. Let us take a value of 5,000. If I take a value of 5,000 and calculate this RTH, I will get this, this number will come out to be 0.00159 Kelvin per watt, all right. So, what do we see? We have got two thermal resistances. The thermal resistance of the condensate film is insignificant compared to the thermal resistance of the tube. That is what we are seeing, all right. The thermal resistance of the condensate film is insignificant compared to the thermal resistance of the tube. Vc, let me write that down. Thermal resistance of the condensate film is insignificant compared to the thermal resistance of the tube, all right. Therefore, now you may say, look, the thermal resistance of the condensate film has only been estimated, because we have taken HO to be 5,000. Suppose we had taken it 10,000, it would be still smaller in fact. You understand? It is in thousands. Whatever you do, whether you take 5,000, 10,000, 7,000, this value 0.00159, we would get a value which may be slightly different, but it will always be insignificant compared to the value of the thermal condensate of the tube, which is 0.190 Kelvin per watt. Okay. Therefore, the total thermal resistance is really 0.190. The condensation does not make a difference, and the outer surface therefore is effectively at 100 degree centigrade, and the flow rate remains the same. You understand? Therefore, the conclusions are the thermal resistance this total thermal resistance, I should say, that is the sum of the two, is equal to 0.190 Kelvin per watt. All right. Temperature of the outer surface is effectively 100 degrees centigrade, and the answer Q by L is minus 157.7 watts per meter. The answer remains unchanged. That is what effectively we are saying. You understand? So, although we have got a situation which seemingly looks different, the thermal resistance introduced because of this new situation is insignificant. The total thermal resistance remains that which we had when there was only one present. It remains 0.190. So, effectively the outer surface of the tube remains at 100 degrees centigrade, and therefore, the heat flow rate obviously is still the same 157.7. Now, suppose you had not recognized this, then you would waste your time perhaps trying to calculate the value of H naught more accurately. from some formula. You may get a value like 6342 for H naught. Would it make a difference to this answer of this problem? No, it would not. Whether you take 6342, which is a more precise value of HO, or whether you use 5000, just does not matter in this problem. In some other problem it may matter, but right now it does not matter what is the value of HO, because the thermal resistance of the condensate film is negligible compared to the thermal resistance of the tube. You follow what I am saying? Always compare the value which is, and say something is insignificant relative to something else. That is the point which I want to make. Okay. So, now we have looked at this situation in which we may have thermal resistances in series, and as I said, it is important to be able to decide which resistance is significant and which resistance is not. Now, we want to turn our attention to another composite situation, a problem associated with another composite situation. We want to look at what is called the critical radius of insulation. That is what we want to look at. Consider again the long hollow cylinder composite situation. Let us say that the inner material here, radius R1, R2, let us say that this is a metal tube, all right. That is a metal tube, and let us say the outer material, thermal conductivity K2, is thermal insulation which is put on the tube. All right. So, it is a composite situation in which one of the materials is the metal tube, the other is the thermal insulation which is put on the outside. On the inside, there is some, in the inside of the tube there is some fluid with a heat transfer coefficient Hi and a temperature Ti, and on the outside there is some other fluid to which heat is being lost. It may be the surrounding air in the room in which this tube is located. The outside heat transfer coefficient is Ho and the temperature outside is To. So, there are 4 thermal resistances, 2 associated with the heat transfer coefficients on the inside and outside, and 2 associated with the tube and with the thermal insulation. Now, this is a composite case for which we know the value of the heat flow rate. From inside to outside, if I want to put down an expression for the heat flow rate, then we will get the following. We have derived it earlier, I am just repeating what we have done earlier. For such a situation, the Q is given by this expression 2 pi L into Ti minus To divided by 1 upon R1 Hi plus 1 upon K1 log to the base E R2 by R1 plus 1 upon K2 log to the base E R3 by R2 plus 1 upon R3 Ho. We know this. Okay. These are the 4 thermal resistances. The first one is associated with Hi, the second one associated with the metal tube, the third one associated with the thermal insulation, and the fourth one with the heat transfer coefficient on the outside. Okay. The 2 pi L has to be taken down in order to call it the thermal resistance. All right. So, it will be 1 upon 2 pi L into all this, then they actually become the thermal resistances. Now, suppose I plot Q against R3. I hold all other parameters constant. What are the other parameters? R1, R2, K1, K2, Ti, To, L, everything else constant excepting R3. Plot Q against R3. Other parameters being held constant. It will sometimes be seen, the value of Q will sometimes be seen to pass through a maximum for a certain values of R3. This value is called the critical radius of insulation. So, if I plot Q against R3, sometimes we will see go through a maximum for a certain value of R3. This value of R 3 we call the critical radius of insulation. All right. Now, first of all, let us find out mathematically by differentiation what is this value of R 3 at which the Q acquires a maximum value. That is very easy to do, it is just a matter of differentiating. So, let us do that. Let us just put down an expression, derive an expression for the value of R 3 at which Q goes through a maximum. Now, in the formula that we put down, okay, let me repeat that. We want to know where this goes through a maximum, this expression. The numerator here is a constant, all right. So, if I want to know where this goes through a maximum, effectively I want to know for what value of R 3 the denominator goes through a minimum. So, let us differentiate the denominator only with respect to R 3 and equate that to 0. Differentiate the denominator with respect to R 3 and equate to 0. The first term, if I differentiate, is going to give me nothing, because there is no R 3 in it, it is all constants. The second term will also give me nothing, it also does not have an R 3 which is our variable, it is going to give 0. Only the third term and the fourth term will give me something, because they have an R 3 occurring in them. So, if I differentiate the third term and the fourth term and equate to 0, I will get 1 upon, I am now differentiating the denominator third term, 1 upon K 2 R 3, that is the third term differentiated, minus 1 upon H O R 3 squared is on differentiation gives me that, and I equate that to 0, I will get R 3 is equal to K 2 by H 0. So, it is at this value of R 3 given by K 2 by H 0 that the denominator goes through a minimum, and therefore, the whole expression for Q goes through a maximum. Okay. We will call this value of R 3 as the critical radius of insulation. This is the critical radius of insulation. So, we will denote it as R 3 critical. This is the critical radius of insulation. Okay. Now, in effect, what I am saying is the following. I am saying, if I were to plot Q, if I were to plot Q against R 3, let us do that. If I were to plot Q against R 3, or instead of R 3, if I were to plot it against R 3 minus R 2, that is the thickness of the insulation. If I were to plot Q against thickness of insulation, that is R 3 minus R 2. R 2 is a constant. So, whether I plot against R 3 or R 3 minus R 2, I will get the same variation, all right. Then I will sometimes get a behavior which will look like this, and sometimes I will get a behavior which will look like this. When do I get the first type of behavior? When does Q go through a maximum? Q will go through a maximum and then go on decreasing if R 2, that is the outer radius of the metal pipe, is less than the critical value which is given by K 2 by H O. if to start with I have a metal pipe and the R2 of that metal pipe is less than K2 by H0, K2 is the thermal conductivity of the insulation and HO is the heat transfer coefficient on the outer surface of the insulation. If R2 is less than this, then we are going to get this type of situation of Q going through a maximum, then decreasing. On the other hand, if the radius R2 of the metal pipe to start with is greater than or equal to K2 by H0, K2 by H0 is the critical radius of insulation, then straight away if I put insulation on that pipe, I will start getting a reduction in Q. You understand? So, keep in mind the addition of insulation on a pipe will help in reducing the heat flow rate if to start with R2 is greater than or equal to K2 by H0. If it is less, if R2 is less than K2 by H0, the addition of insulation will first cause the value of Q to go up a little, then it will start coming down as we go on putting more and more insulation. Now, why does this happen? It happens, it is very easy to see if you look at the expression for Q. Let us go back to that. The expression for Q has two thermal resistances right here. One is the thermal resistance associated with the insulation, the other is the thermal resistance associated with the heat transfer coefficient on the outer surface. The first one, which contains the log to the base e R3 by R2, this increases as R3 increases. The second one, this one, decreases as R3 increases, as you can see it is 1 upon R3 here. You understand? So, up to the value of K2 by H0, that is the critical radius, the rate at which this increases is less than the rate at which this decreases, and therefore, the overall thermal resistance is decreasing and therefore, the value of Q goes up. Once we have got the critical radius, the reverse happens and the overall thermal resistance goes on increasing and therefore, Q goes on decreasing. You understand, that is really mathematically why it is happening in this fashion. So, when we put insulation on a pipe, the lesson to learn is when you put insulation on a pipe, you want Q to go down. So, make sure to start with that your value of R2 is greater than or equal to K2 by HO. If this is so, no problem, whatever the thickness of insulation you put given by R3 minus R2, it will help. If on the other hand, you have a situation in which to start with R2 is less than K2 by HO, then what should you do? You must put enough insulation to see that you have crossed this hump and you have reached a point where the value of Q is less than the value you get to start with when there is no insulation. You understand? So, if I were to take a horizontal line from here, what I am saying is if you have a situation in which R2 is less than K2 by H naught, then you should always put a thickness of insulation greater than the value shown by this arrow. If you put less, you will in fact get a value of Q which is more. So, adding insulation will hurt you, will not help you. You got it? That is the meaning and that is the sum and substance of what we are trying to do when we talk about the critical radius problem. All right. So, now we can look at a problem. I want to solve a numerical problem just to illustrate ideas. I am going to take the following situation. I am going to say, let us say there is a pipe, I am just going to draw a sketch. Let us say there is a pipe like this, some pipe whose inner I am drawing only half of it, some pipe, all right. The inner radius is 0.8 centimeters and the outer radius is 1 centimeter. A pipe with an inner radius of 0.8 centimeters, an outer radius of 1 centimeter. Let us say it is a metal pipe, it is a metal pipe, yes, like this, some metal pipe like this, and we put insulation on the outside of this pipe. We put thermal insulation on the outside of this pipe, all right. This is the thermal insulation. All right, on the outside of this pipe, and let us say the insulation, thermal insulation conductivity is 0.20 watts per meter K. That is the thermal conductivity of the insulation. You are told that on the inside hot water flows and the temperature Ti is 90, hot water at 90 degrees centigrade, hot water flows on the inside at 90, and on the outside there is air at 30, ambient air at 30 centigrade. Values of Hi on the inside of the tube, value of Hi on the inside of the tube given to be 500 watts per meter squared Kelvin, and on the outside Ho, value of heat transfer coefficient given to be 10 watts per meter squared Kelvin. 500 is a typical value for low velocity, water flowing at a low velocity through a tube, and 10 is a typical value for heat being lost by natural convection from an outer surface. All right. Calculate the variation, calculate the variation of Q by L with the Q by L, that is the heat loss rate per meter length, with insulation thickness. That is a numerical problem that we want to do. This is the numerical problem we want to do. It is a straightforward substitution problem. There is no real complications. I just want to illustrate the ideas that we have been talking about. Okay. Now, a typical situation, metal pipe with insulation round it, hot water flowing inside. How does the Q by L vary with the insulation thickness? Now, for this case, if I substitute in the expression, what is my expression? Q by L is equal to 2 pi Ti minus To, all right, divided by the expression is 1 by Ri R1 Hi plus 1 by K1 log to the base E R2 by R1 plus 1 by K2 log to the base E R3 by R2 plus 1 upon R3 HO. That is my expression for the Q by L. Now, the first thing we want to say is we have got a metal pipe made of say steel or stainless steel. What will be the K value? If it is say steel, it will be 10, 12 watts per meter Kelvin. If it is steel, not stainless steel, but steel, it may be 40, 30 or 40 or 50 watts per meter Kelvin. In any case, it is just a pipe, a tube rather, with a thickness of 2 millimeters. All right, R1 is 0.8 centimeters and R2 is 1 centimeter. Whatever the value, the thermal resistance of this metal tube is going to be insignificant compared to the thermal resistance of the insulation. So, straight away let us drop this out and say this we are not even going to calculate it, we are just going to take it equal to 0. I am going to make that approximation, which is a very accurate approximation to make. So, let us forget the thermal resistance, neglect the thermal resistance of the metal tube compared to the thermal resistance of the insulation, which is coming on the outside. It is quite justified. So, with this approximation, what do we get now for the Q by L? If I put in the numbers, I will get Q by L is equal to, if I put in the given data, I will get Q by L is equal to 2 pi into 90 minus 30 divided by, let us put down the data now, divided by, I will get 1 upon R I 0.008 multiplied by 500 plus, neglect the second resistance, the resistance of the insulation 0.2 log to the base E R 3 upon 0.01 1 centimeter, that is R 2 plus 1 upon R 3 multiplied by 10. 10 is the value of HO. Now, for different values of R 3, we can calculate Q upon L in so many watts per meter. Calculate the value of Q by L against with different values of R 3. If you do that, and I want you to do this now, you should get the following answers. Show that for different values of R 3 in meters, all right, I would like you to get the following answers. Show that you will get for different values of R 3 0.01, 0.015, 0.02, 0.03, 0.04. And what will be the thickness of insulation? R 3 minus R 2, which is the thickness of insulation in centimeters, say. So, I will come out to be, here it is 0, because here R 3 is equal to R 2, then it will be 0.5 centimeters, then 1 centimeter, 2 centimeters, 3 centimeters. And you will get Q by L, if you substitute into the above expression, you will get Q by L in watts per meter to be 36.8, 42.2, 43.3, 41.5 and 38.9. And with more thickness of insulation, the value of Q by L will go on decreasing. So, notice now that in this particular case, with the data that we have got, the value of Q by L goes through a maximum, at an insulation thickness of 1 centimeter and a value of R 3 equal to 2 centimeters. You do this calculation yourself, so that you will be convinced of what we have got. Okay. Now, why is this happening? This is happening because Q by L is going through a maximum, because in this case, in the data that we have given, in this case, R 2 to start with is less than K 2 by H 0. That is the critical radius of insulation. And what will we get for K 2 by H 0? We get K 2 by H 0 is, it is K 2 by H 0, in this case the critical radius is equal to 0.2 divided by 10 which is nothing but 0.02 meters, which is equal to 2 centimeters. Okay. So, this is a case where R 2 was less than the critical value given by K 2 by H naught. Therefore, in this case the value of Q first increased, Q by L first increased with thickness of insulation, then decreased and started decreasing. So, this is just an illustration, a numerical example to illustrate all these ideas. Now, a final comment on the critical radius. Keep in mind this situation does not happen very often. When does it happen? It happens when K 2 is high, that is the thermal conductivity of the insulation is high. This situation will also occur when the value of HO on the outside is low. Then the combination K 2 by H naught will give me a high value of R critical, and then only R 2 may be less and Q by L will first go through a maximum. So, it will occur only under these situations, keep that in mind. All right, now on your own I would like you to do the following problem. Please do this on your own and I will read out the problem. The problem is the following: derive an expression, this and the should not be there, derive an expression for the critical radius of insulation of a sphere. Suppose I have a sphere, a hollow sphere, okay, inner radius R 1, outer radius R 2, and I put insulation up to a thickness up to a radius R 3 around it. So, what is the thickness of insulation? R 3 minus R 2. Find an expression for the critical radius for this situation, and your answer you should get is R critical for the spherical case should be 2 K 2 by HO. Please do this yourself in the same manner that we derived the value, this expression for the long composite cylinder, for the cylindrical case. Now, we will just briefly today start with the next topic. I just want to introduce you to the next topic, but we will not really do it today. That is, so far we have taken up one dimensional cases, one dimensional steady state through a slab, one dimensional steady state through a cylinder, one dimensional steady state through a composite slab, one dimensional steady state through a composite cylinder. The spheres case I asked you to do on your own. Suppose all these cases, remember, temperature has only been a function of one dimension. That is why one dimensional cases. They have been temperature has been a function of x or a function of r. Suppose now we want to take up situations in which the temperature varies in more than one direction. Say it is a coordinate system, a Cartesian coordinate system in which temperature is varying in the x and the y direction and the z direction. Temperature is varying in space in more than one direction. Suppose also temperature is varying with time, that means it is not a steady state situation. Whenever we have situations in which temperature is a function of more than one variable, then we need to derive a general differential equation which will be a partial differential equation for solving heat conduction problems. So, now our next job will be to derive the general differential equation for heat conduction for situations in which temperature may vary in space in more than one direction and temperature may vary with time also. All right, that is what we are going to do. In order to do that, we need to consider any time you have to derive a general situation, a differential equation, a partial differential equation or an ordinary differential equation for that matter, you need to consider some element, some arbitrary differential element in that solid and apply the first law and Fourier's law to that arbitrary element. Okay. So, what we are going to do now is we are going to derive a general differential equation for heat conduction. We are going to derive it for an isotropic material, that is a material in which k does not vary in direction, but k may vary from point to point, and we are going to derive it in the Cartesian coordinate system, that is in the x y z system. later on we will generalize to another coordinate system. So, we are going to now derive a general differential equation in the Cartesian coordinate system and for an isotropic material, that is a material in which k does not vary with direction. So, pick an element inside the solid. Let us say the element we pick is an element dx, dy, dz, a rectangular element somewhere within this solid. This is some arbitrary solid, some boundary conditions which we will take up later. This is the differential element. I take a magnified view of it and say this is the direction dx, this is the direction dy, this is the direction dz. Okay? And on this element now, we are going to this element, not on this element, to this element, we are going to apply the first law of thermodynamics as for a closed system. In the process, we will also use Fourier's law of heat conduction and get our general differential equation. So, that is what we will be doing next time.